So as we move on, we're going to rotate to a different variation of problem while working with the normal distribution. Now we know the parameters are mu and sigma, and so far you've been told these parameters in just about every question you've done. But what if we didn't know these parameters and we had to use some other information to try and deduce what these parameters are? So in this case, we don't know the mean, but we do know the probability that x is greater than 20 is 20% or 0.2. So let's just fill in the diagram first. I know where to mark on the diagram to show that there's 20% above this, and that's going to be the necessary x value. Well, can I find a z value that relates to that as well? A z value that has 20% above it. Now, if you remember, we can use the alternate tables to find a z-score that has 20% above it, but also we can just use our calculators and the inverse function, and that gets us a z-score of 0.8416. Okay, so I can also put that on the diagram, so 0.8416. These two values, this real world value or x value and this standardized score or z-score, relate to each other. They're linked to each other, and we know how to connect x values and z values, and that's through the standardization formula. So let's go ahead and use the standardization formula. We'll substitute in our z-score, we'll substitute in our x value. The mean is still unknown, but we were given sigma in the question. Alright, from here it's just a case of rearranging to make mu the subject, rearranging to make the mean the subject. And that gives us a mean value of 17.4752. Alright, just a quick sense check. Does that make sense for that to be the mean value? Well, it's below 20. So yeah, my small indicator, if anything, is that yes, that's a sensible value for us to have as the mean. Okay, moving on. Similar situation. This time round, it's the standard deviation that we don't know. So the width of metal sheets is modeled by a normal distribution where the mean is 50 and the standard deviation is unknown. We'll always write out this distribution. We might be able to come back later and fill in some of the values if we figure them out through our problem solving. We're told that the probability that a width is less than 46 equals 0.2119, and obviously we're out to find out what sigma is. Let's just put this all onto the diagram. These are x values. This is a real world value, so I'm just going to mark that over here as well, and we're going to try and find out what the z score that matches would be. I know that if I have an x value and the corresponding z score, then I can make use of the standardization formula. So we're always aiming to get those things to match up with each other so that we can make use of the standardization formula, so we can make use of one of the tools that we have at our disposal. So I'm going to do an inverse function on the probability there, and that leads to a z-score of negative 0.8. You notice that I usually do z-scores just to 2 decimal places. If we look at the tables, all of those z-scores are usually to 2 decimal places. And that convention just carries through. Okay, so substituting into the standardization formula, I can once again rearrange, this time making sigma the subject. And from all of that, we get that sigma equals 5. Alright, so now I know both parameters of the normal distribution. I could probably do just about any question that comes my way now. And in part B, it just so happens that we've been asked to go ahead and find a value for the 90th percentile. So we're working with the same distribution, but obviously now we've already figured out that sigma is 5. So I'm just going to rewrite that for myself for clarity. And just a quick diagram as always. So 90th percentile, that means a value where there's 90% below it. So where's that going to be? That's going to be on the right hand side of the diagram. So percentiles, if you remember the notation, was to use a p and then a subscript for the number. So p90 in this case, that's the value of 90% below it. So I'm going to go ahead and make use of the inverse function. So inverse 90%, that's on the left hand side, 5 for my standard deviation, 50 for the mean, punch it into the calculator, and that gives us 56.4078. Okay, just one more example to go through. So here we've got a normal distribution where neither the mean or the standard deviation are known. So we've got two unknown variables. And now I'll let you think about that for a few minutes as to what strategy you might be expecting us to use. Going to go ahead and look at the probability statements we've been given. I've been told that the probability x is greater than 35 is 0.025. Okay, so where's that going to be? So over here on the right hand side, this right hand tail is 0.025. Okay, second statement says that the probability x is less than 15 is 0.1469. Once again, where's that going to be? 1469 is quite a small probability, so it's over here in this left tail. And I can label that as well. So I've got two real world values, so two x values. Can I find the z-scores that match them? Can I find the corresponding z-scores? Well, yes, because I know the probabilities involved. So I'm going to go ahead and use the inverse normal function. So inverse normal of 0.1469 for the standardized distribution where the mean is 0 and the standard deviation is 1. That's going to give me the z-score, negative 1.05. I do the same for 35, but I need the probability to the left. Don't forget, it has to be the probability to the left. So 0.975. Okay, and that generates the two z-scores for me, negative 1.05 and 1.69. All right, thinking through again, how can I connect z-scores to real-world values? That's where the standardization formula comes in. Z equals x minus mu over sigma. I'm going to substitute for this negative z-score. That corresponds with 15. And the other two variables are unknown. But let's go ahead and rearrange. I hope you can see where we're going. Now let's actually get all of the variables on one side and the constant on the other side. So mu minus 1.05 sigma equals 15. We can do exactly the same thing for the other pair. So the 1.96, which corresponds with 35. Some rearranging again, and we get a second equation in terms of mu and sigma. We've got simultaneous equations here. Simultaneous equations where we can solve for both mu and sigma. We should have expected this because we can only solve for two unknowns with two equations. Alright, so at this point I really just want you to use the equation solver. Make sure that you punch those numbers in correctly and you should get a mean of 21.9767 and a standard deviation of 6.6445. Once again, really good diagrams are helping us with these questions. We can't just rely on the calculator. We need to get some sense of where these numbers are on the normal distribution to make sure that we match up the correct corresponding values. Alright, from there, just knowing how powerful the standardization formula is and what it does, it converts real world values into z-scores. So whenever we're working with those two, the standardization formula should come right to the front of your mind. From there, noticing simultaneous equations and obviously going on to solve.